Hello everyone. Today is the 58th day of Leetcode 75 challenge. Let's begin with the 58th question. Question 216, combination sum 3. The level of the problem is medium. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. Now let's understand the problem in the easiest way possible. So you are given two integers k and n. Fine. And you need to find all the valid combinations of k distinct numbers such that the sum is equal to n. Okay. So we have to find valid combinations of k distinct numbers so that it sums up to a number given n. Okay, fine. So only numbers from 1 to 9 inclusive can be used in each combination. So for example, they're trying to say that if you're given these numbers only, right? You can use only these numbers. So you have to find, and there would be a k. K could be anything from 1 to 2 to 3 or 2 to 9, anything, right? So if it is 2, and suppose n is 4, okay, let's n be 4, okay, fine. So what could be the combinations? One combination could be 1 comma 3 because 1 plus 3 gives me 4. Another combination could be 2 plus 2, it also gives me 4. Okay, so this has to be the output. So this is what they're trying to say, what we have to do. So our goal is to return all such combinations where the sum of the numbers equals n and the numbers of elements equals k. And also these numbers has to be distinct. You cannot use 1 2 times and then 2 one time, right? You cannot do that, something like that. You cannot repeat the numbers because they said that distinct k values has to be there. If no such combination exists, we will return an empty list and the answer can be written in any order. You can assume that input values for k and n are valid integers and within reasonable bounds. So basically you are bound to get an answer because the values of k and n would be valid integers. The constraints of the problems are k value could be from 2 to 9 and n value could be from 1 to 60. Okay, so the problem is pretty straightforward. So I hope you understood the problem explanation. Let's move to the next slide. Let's understand the input output of the problem. Suppose if you get C here, k is 3 distinct elements and n is 7. Okay, so from 1 2 3 4 5 6 7 8 9. Okay, from here if you take 1 2 and 4, it sums up to 7, right? And there are three distinct numbers. Is there any other case we can take? We cannot, because if you take 4, you can then you can take 3, then you have to take another number, which is not possible here, right? So therefore only one combination is only possible in this particular case. Now in example 2, let me write one 2. Here if you could see, we have to take three distinct numbers and sum has to be 9. So here they have taken 1 2 and 6. 1 2 and 6. 6 plus 2 8 plus 1 gives 9, right? And 1 3 5. 5 plus 3 gives 8 plus 1 gives me 9 again. 2 3 4. 2 plus 3 gives me 5 plus 4 gives me 9, right? Is there any other combination possible? Let's try taking 6 uh, plus 2 plus 1, which we have already taken. If we take 7, then plus 2, it already gives 9. If we try to take 1, it gives 8. So there we cannot take any other numbers, right? So only three possible combinations are only there for this particular case. Okay, so I hope you understood the input output explanation. Let's move to the next slide. Before going to the further slides, let's understand what backtracking is. Okay, backtracking is a systematic way of exploring all possible options to solve a problem by building a solution incrementally and abandoning paths that fail to meet the constraints. Okay, basically in backtracking you explore all the ways. Okay, suppose if there is a number 6 and it has to be multiplied by 10 values. Those values could be anything, so you will be exploring all the possible ways, right, to find out which gives me the specific product. Okay, by building a solution incrementally and abandoning paths that fail to meet the constraints. Okay, so how it works is basically start from an empty path or an initial state, choose an option or pick a candidate or take a step, right? Check the constraints if the partial solution is still valid or not. Recursion to the explore further with current option. If it leads to a valid solution, store it. If not, backtrack, undo the choice, let the next possibility repeat until all the paths are explored. So to understand, we can take an example like finding all binary strings of length 2. Let's just take an example, okay? So what it could be, we have to generate all possible strings made of 0 and 1, okay, which is length 2, okay. So what we gonna do, we're gonna start with, let me clear this up. We will start with an empty string, correct? Then in each step you can choose 0 or 1, right? Because our aim is to find all binary strings of length 2. What is binary? Binary is 0 and 1, right? So combination could be 0 0 1 1 1 0, 0 1, whatever, right? So we start with empty string. So at each step we can choose 0 or 1, right? So what happens if we choose 0 in one step, right? Then in next step with this 0 we can choose another 0. So this becomes one of the case, right? Then with this 0 you could take 1 also, right? Now similarly, instead of taking 0 you took 1. Then you have the option of taking 1 with 0 and 1 with 1, right? So these are your possible answers, correct? So if you go much more further, the length will increase to 3, right? That is our base case. That is what is written in point number 6. If not, backtrack unto the choice and try the next possibility. So if we go for further, there would be more cases, right? 0 0 1, we don't want that. Therefore what we do, we backtrack, correct? So that is what a backtracking works. You go back, right? Then you start again. And why it is efficient? Because the time complexity depends on the number of recursion branches. Example, O 2 to the power n for subsets, O of n factorial for permutations, okay? And space complexity is O of n always, because this is a recursion stack space, because the recursion always takes a stack space to store the solutions, okay? Now these things are efficient for reducing the brute force search using pruning, exploring solution spaces exhaustively, but only when necessary, okay? So I hope you understood the backtracking concept. Let's move to the next slide. Now, where backtracking is used, it is used in combinations and permutations, building a set of numbers or characters. For example, you can practice question number 39 from Leetcode, combination sum, permutations, 46 question number, right? It is using n queen problem. It is a very famous problem. Place n queens on n cross n board with no two attacking each other, or no two queen attacking each other. Okay, this is a classic CS backtracking problem. You should definitely practice this. Sudoku solver, we fill a 9 cross 9 board so that every row, column, and 3 cross 3 box contains 1 to 9 exactly once. Basically, we code Sudoku here. Okay, problem number 37. We use this backtracking in the subset and combination with constraints problems, where we have to generate all the valid subsets in a given specific rules. You could practice problem number 90 from Leetcode subset 2 or combination sum 3. Backtracking is also used in word search, pathfinding in grids. You could practice question number 79, word search, which will help in searching for sequence in 2D grid. So this is all about backtracking and its concept. I hope you understood it. Let's move to the next slide. To understand what problem is asking, we should build up an intuition to the problem. So let's start by understanding the goal first. Okay, you are given two integers k and n, right? And our task is to find all unique combinations of k numbers that such that sum up to n. Okay, we have to take exactly k elements, which has to be exactly equals to n. Their sum has to exactly be equal to n. Okay, only numbers from 1 to 9 can be used, and each number can be used at most once. Okay, so basically in one combination, one can be used only once. You cannot use it two times. That what they mean. For example, if k equals to 3 and n equals to 7, the value combination is 1 to 4. Okay, so this is clear to us. We must return all such combinations without repetition and in any order. Okay, we're free to return in any order. So the brute force approach is trying all possible subsets of 1 to 9 and check for the two conditions, size equals to k and sum equals to n. But this is inefficient, because in the brute force solution we generate all the subsets from 1 to 9, right? For each subset, length will be k and sum will be n, right? And we have to keep that. This ensures that we check every possible subsets. So there are 2 to the power 9 subsets, 512, right? Since each of 9 numbers can be either included or not. This is feasible, but this is not efficient. If we look for the efficient solution, which I will be talking about in next slide, this is an inefficient one, right? So because of this, the time complexity becomes exponential, and that is a very large number. Okay, so to find the efficient solution, we should look to the next slide. Now, since they are asking us to generate all the combination, the first thing which should come to our mind is recursion. Okay, yeah, it also takes an exponential time complexity, but here we will be using backtracking. Keep that in mind. Okay, in previous brute force, what we were doing, we are going for every solutions, even which are not considered to our sum, or which is not a proper combination, right? But in backtracking, we know that if some of the things does not go as planned, we just go back, right? And we don't look for the other combinations, because we know that if this is not possible in the worst case scenario, these are not in our paper to work on, right? So let's see how we're gonna, you know, understand this particular thing. So we know that it will be starting, I will be starting from 1, right? We know that, and there would be a sum. Okay, that will also be starting from 0, of course, and it has to be equal to n. Okay, so what we could do is that, uh, if I equals to 1, right, and there are two scenarios that can be possible, that are those are which are possible. One is, either you could take this I. Okay, now sum is also 0, and no, the value is 0 right now in the subset, and n is here. Okay, okay, n is the total sum. So one case is you could either take or you cannot take. Okay, so if you take, what will happen? I will become 2, definitely, and in subset we will be having 1. You could just, I will just write 1 here. Okay, and sum will be whatever sum is there. So suppose, if it is 6, I am taking 6 in here. Okay, so it will be 6 minus 1, right? Because you have taken 1, so it will become 5. If you don't take, what will happen? I will become 2, correct? And everything will remain 0, n 0 and n. Fine. Now from here also you have two scenarios: either you could take or you cannot take. Okay, or if you don't want to take, you could say that way. So now I is 3. Okay, and okay, I have not considered the k value. Let's take, since n here is 6, and let's, I'm taking a random value here. Let's k be 3. Okay, let's see if some combination is generated or not. So if you take, so what will happen? If you take this 2, it will become 1 comma 2, right? I will draw this, and 2 will be subtracted from this 5, and it will become 3. And if you don't take, what will happen? It will remain as it is, right? Again, you have two options. If you can see here, if you take 3, I becomes 4 here in this case now. If you take 3, it becomes 1, 2, 3, and total sum becomes, n becomes 0 now, right? And if you don't take, it still remains 1 comma 2 and 3 here in the case of 4. Now, if you could see here, the thing is done, right? We got the combination, one of the combination we got, which is, let me write somewhere. I will write it here. Okay, 1, 2, 3. Okay, so what will be the base case for our backtracking or the recursion to stop? If you could see, if our n becomes 0, because we are subtracting the n itself, right? First case. Along with this, if the subset which we get here, if its length of, let it be temp. Okay, if it is equals to n, okay, okay. So if these two conditions satisfied simultaneously, that n is also 0, which means the sum becomes 0, and length of the, that subset which we generated is equals to k. So there and there itself we will return, we will store the answer, and we will return. Okay, store and return. And when we will go back, we will keep on popping these values from the temporary array, so that when we go or explore this particular part, we can push 4 into the in our particular scenario, right? That is why we pop it from our temporary array where we store the subset, and we go back. Then we come here again, we store the values, and again we do the same take and not take case. This is completely a recursion problem. So if you have the understanding of recursion, this should be very easy for you because it's a very simple question. And why we are trying to pop it from our temporary array when we go back, because if you don't pop it, the temporary array will keep on storing the every values in it, right? And it will give a vague answer which is not correct. So whenever we get a solution, like here we got 1 2 3 as a subset, we know that okay, it's a full and final answer. And if we try to explore more in the left and right hand direction, there might be a chance that there is a chance that we won't be getting the particular answer, right? Because if you take any other value other than 1 2 anything like 1 2, if you take 4, suppose you have taken 4, right? Because this next value has to be 4, some becomes 7, right? So that is why we store the answer and return back, and we pop the 3 from the particular temporary array, so that we can go in the not take case. I have written the not take initially here, but it will be like going back and then generating the not take case. And then in that particular scenario we will be having only 1 comma 2, and in that case we can put 4 here, right? Since here if we see that we have all the 3 values, but the sum is not equals to 0, right? So what will happen, we will pop this particular thing and we will go back again, and then we'll go back again, and then we'll start from here, right? This is the way how the backtracking and recursion would be working. So if you could see here, for example, level 0 pick 1, level 1 pick 2, level 2, like these are level 1, level 2, and this will be level 3, right? Level 2 pick 6. Okay, so 1 plus 2 plus 6 gives me 9. Valid backtrack to other paths like 1 3 5 2 3 4 etc. And if you could see here, the size of the temporary list becomes k, and sum equals to n, or basically n becomes 0, right? We found a valid combination. Then we instantly backtrack, remove the last number, and try the next one. Got it? This is a simple visualization process. I hope you understood it. Let's move to the next step. Now, how are we going to simulate this particular process, right? We will use a recursive function helper with the name of fun, right, to explore all the combinations. Okay, and the function will keep track of the 5 things. Now, the base function which will be given to us, in that function we will generate an array which will have 1 to 9 numbers. Okay, so because we have to know, right, that we have to check it from 1 to 9, that um, because we will be taking each number every time, correct? That is why we need an array for that. And also we will try to store the value, the final result or the subsets in an answer, which will be a 2D kind of an array or list. Okay, then we'll call a function, and that function will be having what? That function will be having fun array, this one, having 1 to 9 numbers, correct index which will be 0, then length of the array. Yeah, I know you could just write 9 also here, but putting this makes much more clarity to the question. Then answer, where we will store the all the subsets. Then and temporary array also we will pass it this in this form, k and n, right? Now this will be the main things which will be passed in our function, recursive function. Now in those that recursive function, as I said, we will be having a base case scenario which will be having like if n equals to 0 and the length of the temp array, if it has all the key elements, what we'll do, answer dot push or append in Python the temp, right? Otherwise, if this is not true, we will just return it from there. That's all. Okay. So this is the way we will be doing our code. So let's move to the next step now. Now what we figured out? We figured out that backtracking allows us to explore all valid number combinations without repetition. Proving early when the sum exceeds n or length exceeds k improves efficiency, because in a brute force solution we were not doing this particular thing, right? We were just exploring all the possible ways, and that was going a lot, right? Using numbers in increasing order ensures uniqueness and prevents reuse. And only combinations with exactly k numbers summing to n are added to the result, right? So this is what we figured out from our intuition. So I hope you understood the intuition. Let's move to the next slide. Now, since we got the intuition of the problem, let's look into the approach how we're going to solve it. So first thing, we will check this is the function within the fun function, right? That length of the subset is equals to k and n is equals to 0. If yes, we return an empty list. Actually, not the empty list. It's a typo here. We'll just return the complete list and store it into the answer list. Otherwise, if this condition is falsified, okay, If subset is equals to and n is equals to 0, we will store the complete answer like this. I will write it here. Just ignore that part. Let This is the subset which we got. If it is equals to the k and n is equals to 0, just put answer dot append the subset. This is what we will do. Otherwise, if this if condition is falsified, then we will just return from there. Okay. Now step 2, we prepare the input. This is done in the base function which is given to us. We create a list array 1 to 9 representing available numbers, because only numbers 1 to 9 are allowed and each can be used at most once, right? Now in the start 3, in the fun function, we will initialize an empty list answer. This will be done in the base function. Not base case, base function which is given to us already. In there we will call the helper function fun like this, self dot fun. There we will be having array of 9 numbers. 0, this is the index, current index. Temporary array, which will be this way, then k, then n, right? These are the things which we will be passing in the fun function for our recursion. This setup allows controlled recursive exploration starting from the smallest number, right? Now at this step 4, within the fun function which we have created, this is the base case as I already mentioned previously, right? Then the recursive case is that if the array of index has to be less than n. This is one more thing, because if you are in an array and your n or the remaining sum is 3, suppose this is 3, right? And if you are standing at 4, it is not possible to take 4, right? That is why we have to always check before doing the recursion that if the array of index is less than or equals to n or not. Okay, if it is, right, so what we do, we append to temp. The function goes this way: if array of index, okay, if it is less than equals to n, then within this case what we will do, in temporary we will store this thing like append array of index, okay. Then we will call the recursion fun, which will be having array, simple, increase the index, of course, since 1 is taken we will go for 2 now. Then the size of the array, okay, which is 9 here. Then the answer, then the temp, then k, then n minus array of index, right? I hope you understood this, because if suppose n was 8, we took 3, so it has to be 5, right, in the next recursive call. That is why we've subtracted from the given number. Okay, so this is the way which we do. And when this is done, when this particular if condition is done, or if this condition is false, right, we write the same function again, same thing again, just we don't write this particular case, we just write n there, because since this was not possible to take, so there is no use of subtracting array of index from it, right? Let me write it. We will look into the code. Okay, I will explain there much clearly, right? That is done. And after this complete recursion is done, we just return the final output, which is the answer. Okay, so I hope you understood the approach explanation. So let's move to the next slide. The code is the exact copy of the approach discussed. Let's understand it line by line. So if you could see, we have generated an array here from 1 to 9, an empty list for storing the subsets, and we call the function here. Now if you could see, we have the array, we have the correct index, we have the size of the array which is 9, okay. Answer to store the subsets, temporary to store the current subset, k, and the sum, okay. Our base condition says that if index is equals to s, which means that if we have reached 9, okay, we have reached 9, that we have explored all the parts, okay. If we have done that, then just come here, because if you remember the tree, even if we were standing at I equals to 3, we used, and we got the stuff, right, then we used to return back, right? Otherwise, if it was not fulfilling the condition, what we were doing, we will popping it and we will coming here in the next case, and in I equals to 3 not take case, right? And from there we used to go more deeper down, right, like I equals to 4, I equals to 5. So this particular thing saves our iteration for this particular scenario, right, which was the extra time complexity. So that is why we have to explore all the I values from 1 to 9. That is the must thing, but this is what we have made our code efficient by removing this particular scenario. That is why when and only index becomes s, and becomes 0, sum is 0 basically, and we have all the k elements in our subset. We just append that particular thing into our final 2D list and return from there. Okay, and even if this condition is false, we just return. Okay, now after this base case, if we have not reached the base case, in that scenario, as I discussed, array value has to be less than the n or the sum. We append that value in the temporary array. We call the function for the next value, and after this particular thing is done, what we do, we pop it from our temporary array, as we know when we go back, right, so that we could put in much more other values also to explore new subsets. And if this condition is false, okay, what we do, we just move ahead, but we don't decrease the sum. If you could see, we are decreasing the sum here because we are not taking any values in this case. This is a not take case, so we won't be declaring reducing the value. Okay, so this is the way the code will work. Now the time complexity for this particular code is 2 to the power 9, which is exponential, but which is 2 to the power 9 gives me 512, right? So this is within our time complexity limit. So this is an efficient solution using backtracking, and the space complexity becomes O of k because in temporary we are storing k elements, right? That is why. And why 2 to the power 9? Because for every one, for one, we are going for every 2 to 8 cases for each scenarios, right? So that is why the total combinations becomes 2 to the power 9. So I hope you understood the code explanation. Let's move to the next slide. Now, since we have the understanding of the code, let's look at the dry run of the example. So for our understanding, or better understanding, I have brought down the code here so that we could match it with it. Okay. So let's start. So here k is 3, n is 9. Okay. So we have this particular thing here. Let this be 9 and let this be 3. Okay. So I could write it here also, k equals to 3 and n equals to 9. Fine. Now how it starts? We call the function first. Okay. Now I is, let me write this also, 1 2 3 4 5 6 7 8 9. Okay. uh, ind is standing here at 1, or I could represent ind as I. Okay, please keep that in mind. So I is standing here. Great. So first, when we call this function, the base case are checked. So of course the base case gets falsifies here. Then we come back here. Now array of index, I value is 1 right now, right? So an n value is 9. Let me write it here. So is it less than this? Of course it is. So in the temp array, we will push this one and we will call idx plus ind plus 1, which means I will be standing here, and n value would be changed to 9 minus 1 gives me what? 8, right? I will write it 8 here now. Now 8 is passed here. Okay. Now again the base cases are checked, falsified. Now array of index, I value is 2 right now, correct? Is it less than 8? It is. It is. So what we'll do? We'll append it into our temporary array. Okay. Then we will increase the I, and then we will subtract this particular value from the n. So it will become 6. Okay. So again we will come back here since it has become 6 now. Again base case are checked, falsifies. Now array of index is what? Array of index is 3. Is it less than 6? Of course it is less than 6. So we will put it in our temporary array. Then after that we will try to increase the index to 4. Okay. And the value will be decreased. So 6 minus 3 gives me 3. Fine. So when we come back, we check, okay, if index value, if it is equals to s. What is s here? S is length of array. What is length of array? Length of array is 9. Okay. So it is not equal to that the particular value. Fine. So this becomes false again. Here array of index. What is array of index? Array of index is index value is 4, right? Is it less than n? No, it is not, because we have 3 right now and we are standing at 4. So this condition is not calculated. Then we come back to this particular function. Then here what we do, since we cannot take that value, what we do, this index plus 1 is done. Come here and just that's all. Okay. Again the function call is made. Again we know it is 6, right? Not 6, it became 3, right? I forgot to update this. So again it will check index equals to s, becomes false because index is standing at 5, not 9. So again it will come here, array of index is less than n. No, it is not because it is 5, right? So again index plus 1 is done. So again the similar process is done because you know that all the values here are greater than 3, right? Now when we are standing at 9, index equals to s, true. Is n equals to 0? No, it is not. So what we do? This becomes falsify. So we don't store it anywhere. We just return from there. Okay. Now when we return from there, what will happen? Just imagine here. Since I'm not drawing the tray, we'll come back. We'll come back from here. We'll come back from here. We'll come back from here. We'll come back from here, here, here. And when we reach 3, you could see when we reach 3, this thing is called, right? So temporary dot pop is done. So this is also popped. Okay. Now when this is done, what happens? Again the functions are called with since 3 is subtracted, right? So we have 6 now. Now 3 also gets back to 6, right? Because when we pop that particular value from the temporary array, so the value also has to be increased, the sum. So sum becomes 6 now. Again this function call is done. Now it is not true. Now we are standing at 4. Okay, because this case was 3, if you remember. 3 is done, so we go to it was 4 because we have taken 3 from above, right? But this becomes wrong, no, out of bound or something like that, right? It falsified now. So we come back to this particular scenario with the value 4. So we are standing at 4 now. Is 4 less than or equals to 6? It is. It is. So what we do? We push it here. Okay. Then we increase the index to 5. Then we subtract n minus 4, which is 2 now. So it will become 2 everywhere. So this thing happens again. Okay. Now what happens? Now we will come here. We will check. Okay. So array of index is not less than 2, right? And similarly, we know that this complete thing is greater than the particular value. So when we will reach 9 again, we will check. Okay, n is not 0, but temp is equals to k. But this is a AND scenario, so it is false. So what we do? We return again back. So when we return back, we come to 4. Now what will happen? We'll pop 4 from this particular temp dot pop. Okay. When we do that, our sum becomes, the n becomes 6 again. Okay, since we have removed it. Now similarly for the 5, same scenario will happen. I'm skipping this part right now. Then again we will come to 6. Okay. Now when we come to 6, we will see, okay, it is equals to less than n, right? So we push it into our temporary list. We call this function, I comes to 7 now. Okay, we see that index is not equals to the 9. So again this scenario is done, but here we could see that array of index, which is 7. Okay, I have forgot to update this. When we push 6 into our temporary array, it should become 0. It is 0. Okay. So 7, of course, it is not less than 0. So we don't do anything here. We just increment. Again, it is the same scenario. This will become false. The same scenario, right? I'm skipping those parts. So now I is equals to 9, right? And we are standing at this particular scenario. N is 0. Yes, it is 0. Is length of temp equals to k? It is, because it is 3. So in answer array, we will push this 1 to 6. Okay. And then what will happen? Since this one thing is done, right? If you could see, if we have the knowledge of recursion in a proper way, we were just popping out this last values because 1 2 was satisfying the condition. The main condition was 6, the last third value. Now what will happen? This particular thing is done. Okay, we'll explore everything with 1 to 6, 1 2 and 1 1 2 then till 9 here, right? Now we have to explore new values. So what will happen? This will also get popped because we will revert back to 2 here. Okay, we will revert back to 2 after this push value, pushing the temporary. Now we won't be taking 2 with 1, we will be taking 3 because I was standing here. Now I will start from here. Okay, now again the same thing will happen. Again we will take values from 4 to 9 and the same thing will happen. So I am keeping those two subsets for you to try out, so that it makes you much more understandable to the question or the solution which we have come upon. So this is the same way it will happen, and again we will get here 5. Okay, we'll put that here 1 3 5, right? And then what will happen? Think about it. Again it will pop this 5. Okay, again it will pop 3, because 3 5 combination is done with everything, right? So again what will happen, we will pop push 4, then with 4 from 5 to 9 we will push, then we will push 5 here, right? Every combination will be checked, and after that, after checking all those combinations, the one combination with 1 will be completed. Now our I will start from, if you have guessed it, it's correct, it will start from 2. It will start from here, right? Then again 2 with 3 4, like this the combination will start. So this is the way the recursion will go. I will highly recommend you to draw the recursion tree for this particular scenario for the dry run. Now if you have any doubts or confusion about the solution we arrived at and how we arrived at it, I would suggest going back and understanding the intuition, the approach and the code, and along the backtracking recursion concepts if you don't know. After that, do a dry run by yourself on 2-3 examples, and I'm pretty sure you will understand both the solution and the thought process behind it. So let's move to the next slide. Now, since we are familiar with the problem and the solution, let's move to the Leetcode and code the solution. So first, let's start by generating this array 1 2 3 4 5 6 7 8 9. Answer to store the 2D list. Then we will call the function with what? Self.fun. We will be having the array. We will be having current index, length of the array, or you could pass 9 also if you want. Okay. Answer to store the final answer, empty temporary list, k and n, right? And after that, what we'll do? We'll just return answer from here. Great. Now we will create a function here, def fun self array index s, then answer temporary array k and n. Fine. Now we will start by writing the base case. If index is equals to 9 or s, right? Then we will check if n is 0 and length of the temp is equals to k. Okay. Then what we will do? Answer dot append the temp, okay, and just return. Okay. If otherwise, if array of index is less than equals to the remaining sum or n, we will call the recursive function. We will first push the value temp dot append the array of index, then self dot fun array will be there, index plus 1 will happen, s answer temp, everything will be same. Okay, just we will change n minus array of index. Okay, otherwise this after this, when we backtrack, we will pop that value from the temporary array. Otherwise, if the condition is false, self dot fun array index plus 1 will happen, of course, s answer. This is not take case, okay, and k and n. Fine. So this is our code. Let's try submitting for the sample test cases. Okay, so there is a mistake here. Let me check. Okay, so the mistake was we cannot just push the temporary array or the list into another 2D list directly this way. We have to write it this way so that all the values of this temporary is taken. Okay, so this was my mistake. So let's try submitting the test case now. So we have successfully submitted the sample test cases. Now let's finally submit the solution. So we have successfully submitted our solution. Now code of the problem is available in my GitHub repository. You can find the link in the description. Thank you everyone.